Okay, welcome again to the European Non-Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Arne Van Antwerpen from the Ghent University. The title of his talk is Indecomposable Symptoms of the Yang-Baxter Equations. Please.
Thank you very much also for the invite to give a talk here. So today will be an exposition on a bit of joint work I did with Colazzo, Eric Jespers, and Kubat, and some tools and methods we used throughout. So to put everybody on the same page, let's start with the definition of a set-theoretic solution. Most people will probably have already seen that. So we say that X is a non-empty set, and we take R, a map from X times X to X times X. Then we say that the tuple XR is a set-theoretic solution if, well, R times the identity on X, the identity on X times R times the identity on X is equals to something, so that is an equation on the set X to the third, is equal to, well, if we start with the identity on the left, so identity times R times the identity on X, identity on X times R. What we will also ask is that this map has to be a bijection. That is something I don't always ask, but for this talk, I will for sure use that. So that's called the set-theoretic solution of the Yang-Baxter equation. And we will later just call that a solution. What more? Well, to have some notation, let's denote the image of a tuple xy, so elements x and y in X, as, well, on the first component it becomes lambda x of y. On the second component, this is rho y of X. Then we look at the subclass of these R's, which are nice, on which you can easily use groups, the so-called left and right non-degenerate ones. So we say that a solution XR is left or right non-degenerate if those maps lambda x or the maps rho x are all bijective for all x in X. And what we will look at in this talk, and what we've looked at in the paper, is to assume that the set X is finite and that the solution is indeed both left and right non-degenerate. All right. So some examples of such solutions. Well, where do you find these solutions? Maybe I should discuss that. Where do people use or see these solutions pop up? Well, they come originally from mathematical physics. In, well, the work of Yang and Baxter. Also in dynamical systems, they are very much present. It was, I think, related to one of the two. Where they also pop up are in Hopf algebras, and in particular for the Drinfeld quantum double. Of course, it shows up in knot theory because the equation I just wrote down is compared to the so-called quantum Yang-Baxter equation, the composition with a twist. And what I just wrote down is the rate equation. So People might know that as the Ramirez tree move. So also in knot theory, they show up. They're a bit throughout a lot of mathematics. Some examples, easy examples. Well, the first one that might pop up in your mind is, well, a boring one, just the identity, is an example of a solution of the Yang-Baxter. Secondly, doing slightly more. This is, by the way, not left and right non-degenerate. I'll note that down. It's important to remark. So in the remainder of my talk, they don't show up the identity at all, not left and right non-degenerate. What is like the main example, the easiest main example for us is the twist solution. So just twisting the two components. Slightly more involved is if you take a permutation of your choice on the set X, you can define the map Rx of Y as sigma of Y, sigma of X. Perfectly aligned. Also a nice solution of the Yang-Baxter equation. This is also a solution with a special name. These solutions are called, or are special cases of Lubashenko solutions. What he does, what the general version of that is to allow a second permutation and change the second component by this permutation, but then you need to assume that these guys commute. So indeed, if I take those two maps just as the same permutation, for sure they will commute, for sure they're Lubashenko solution. Finally, if you take any group, you can construct a solution. There are many ways you can do that, but for our talk, the most interesting way is in the following. You take a G and an H in your group, you send that to H inverse GH. So somehow your solution just measures the conjugation in your group. These solutions are closely related to knot theory because they show up as racks and quantles. What the precise definitions of those guys are, I will not give them. It's just, if you're interested, you can look up those terms. All right. So that are some examples. And of course, you need to know when two solutions are the same thing. You need to define isomorphisms and morphisms of solutions. So let's also just quickly give that a definition. It's the thing that looks very natural to do. Just take two solutions, XR, YS. Then a map between the sets X and Y is a morphism of solutions if the following square is satisfied, so is a commutative diagram. You have your original solution on X, which is R, so X times X to X times X. You have the map S, which goes from Y times Y to Y times Y. And you have maps from X to Y. So you can consider this. Just taking F on both components and also taking F here on both components. If that is a commutative diagram, then you say that this F is a morphism of solution. And then an isomorphism is of course, when that guy is bijective. I told you I gave you some examples of set-theoretic solutions. You might not yet be convinced that there are a lot of them. And for that, I have some numbers today. These come from another paper by Ogun, Merep, and Vendramin, who show that there are indeed a few solutions. So let me just write down their names. It gives you a table. So let's take the size and the number of solutions. And let's start at 4, 5, 6. Then I might need some more space, 7 and 8. For 4, so of size 4, there are exactly 230 non-isomorphic solutions. Still nice and comprehensible. For 5, there are 3,519 non-isomorphic solutions. For 6, we have 100,071. For size 7, there are 4,602,720. And in size 8, which at the moment, as far as I know, is the largest computed number of non-involutive set-theoretic solutions, is 442,000. 400 million, my apologies, 449,480. So it's clear that very, very fast these guys blow up. And that there are a tremendous amount of set-theoretic solutions that indeed are both left and right non-degenerate and are bijective maps, as we requested. So instead of looking at what the properties of all these solutions are, because that might be unfeasible, it might be interesting to start looking at smallest components in some way, like we tend to do in a lot of parts of mathematics, particularly in algebra. You try to take the simplest part, smallest part, that is for you relevant, and study that. And for that, we come to the definition of decomposability. And it for sure goes back to the seminal paper of Ettinghoff, Schettler, and Soloviev. At the end of the 90s, which say that the solution, they define it for involutive solutions, but we don't need that. The solution XR is decomposable if is written nicely, if there exists a partition of the set X into two parts, Y and Z, such that, well, Y and Z are both non-empty, and Y are Y times Y, so the restriction of R to Y times Y, and Z with the restriction of R to Z times Z are subsolutions. Good. That will be sufficient. Some folklore. I didn't immediately find a good reference for this, but it's for sure well known. Is that you can reformulate that in terms of morphisms in the following way. If you had, so I'll write it down as a folklore lemma. Your solution is decomposable even only if there exists a morphism F from your solution to the solution on two elements with tau. What is tau? Tau in the remainder of the talk will just appear once or twice, maybe still. It's just a twist. So you need to have not just a morphism, important, forgot part of the word, an epimorphism. So a surjective morphism to 0, 1 with the twist solution. Will be the same thing. Of course, if you look at this lemma, you can start wondering, yeah, sure, but you're looking at a morphism of two solutions, of two elements with a twist solution. Why not just generalize that a bit? And that might come up in the second part in the later part of this talk on indecomposable solutions. So the idea is we want to know more about solutions that are not decomposable. We say XR, a solution, is indecomposable if, well, it is not decomposable. So it is in some way the smallest constituent. There is no partition of X which fits it into two subsolutions. They're at the moment, very hard to approach, to really classify all of these. You, of course, have some characterizations of indecomposable solutions in terms of actions of groups. Maybe a bit more on that later, but let's look at particular examples or a class of examples, which are the simple solutions. So what is that? Well, it's the similar idea as in group theory. You remember a simple group is one without any normal subgroup, non-trivial normal subgroup. Well, sure, but within solutions, it's hard to talk about a nice subsolution or a normal subsolution. The moment, as far as I know, there is no satisfactory definition of these things, for sure, not in general. But what you can look at is look at the other characterization of a simple group. It has no non-trivial epimorphisms. So we say that if XR is a solution, then XR is simple if, well, for every epimorphism from X to Y, with the size of Y strictly smaller than the size of X, one has the size of Y has to equal 1. So it's just the solution with one element, which of course, this morphism you always have. Your first question might be, okay, do these guys exist? Small note maybe is indeed, as I said before, these are special examples. So if you are a simple solution, you're for sure indecomposable. Because decomposability was having a particular epimorphism to a set with two elements. You don't have any epimorphisms, so you are indecomposable. Well, you have to exclude one case. If the size of X is not 2, and for good measure, exclude also the case that the size of X is 1. All right, so let's come back to that example that I promised. An easy example of both an indecomposable solution and in some cases simple is take a particular permutation. Let's now say the n cycle 1, 2 to n. And I look at the set X, which is just 1 to n. I define Rx of y as sigma of y, sigma of x. Then this solution is indecomposable. for indecomposable. For all n, of course. When is it simple? Well, I think we all feel that it will be simple. Simple if your choice of n is a prime. All right. Good. So these are examples, Lubashenko examples of both indecomposable and simple cases. Are there other constructions or easy constructions of simple solutions? Unfortunately, the answer on easy or relatively natural is no. There are a few beautiful examples with often infinite families by Sdo and Okninsky. But at the moment, there is no general framework how to really obtain simple solutions. So they have a few papers on constructing simple solutions. What we will be looking at is how to identify whether a solution is simple later on. But for that, we need another player, an algebraic structure, which is called a skew brace. So the definition is as follows. A skew brace is a triple B plus circ, where B plus and B circ are groups, and for every A, B, and C, in B, we have that A circle B plus C is equal to A circle B minus A plus A circle C, where minus A denotes inverse of A in B plus. These algebraic structures came up in the study of set-theoretic solutions, even in the construction of set-theoretic solutions, and they turn out to be very important. They were, well, a particular version was first introduced by Rum. That's maybe also an explanation of where B plus, in particular the plus symbol, comes from. For him, he took abelian groups B plus. For us, that does not have to be abelian. That generalization was done by Guarnieri and Vendramin. So Rump introduced what we call a brace. Guarnieri and Vendramin extended that to skew braces. So why are they interesting? Well, because you can show that, how can you easily do that? They give you set-theoretic solutions. So if B plus circ is a brace, skew brace, then the map R A of B defined as follows. So minus A plus A circle B, comma, what's the easiest way to do that? Maybe do that. So minus A plus A circle B, bar circle A circle B, where an element barred means the inverse of C in B circle. This will turn out to be a set-theoretic solution of the Yang-Baxter equation, both left and right non-degenerate. And it's very useful to construct these solutions. Some examples of skew braces. Well, you can take any group. Then if you just take the same operation twice, this guy becomes a skew brace. This is often called a trivial skew brace. You can think of other slight modifications of this, similar to what you would maybe do in ring theory, by considering opposites of in one of the places you have almost trivial skew braces and friends. Next, a slightly less trivial example is a skew brace on D8. So for me, D8, that is a dihedral group on 8 elements. So generated by A and B. A to the fourth is B squared is 1. And AB is BA inverse. This guy will be my multiplicative group, or the circle group. What do I consider for the additive group? Well, the additive group, so it's a bit weird what I will now note down. Now I think about it, because it's D8 plus is isomorphic to C8. Maybe I should put some quotation marks around D8. I just consider that a set there. In what sense? Well, this will be generated by the element B. In what way? How do I identify the elements of those two groups? Well, an element that I would here denote by A to the I, B to the J, in my cyclic group C8 generated by the B's, I would consider this 2 times I plus J. Of course, here I assume that I sits between 0 and 3, J sits between 0 and 1. So A corresponds to 2 times B, AB corresponds to 3 times B, etc., etc. It's a nice example of a skew brace. You can do this for any dihedral group in this way, with then a cyclic group beneath it on the additive as the additive group. And then comes the second reason why skew braces are so important, because you can construct for any solution an interesting group, which we have called a structure group, or the Yang-Baxter group in some papers. You take the group generated by all elements in X, and you set the relations xy is uv if R of xy is u comma v. So it encodes the combinatorial data of your set-theoretic solution. This will be, let's just quickly abbreviate that by G. This will be the circle group of a particular skew brace, which some people call the structure skew brace of the solution XR. What is the additive guy? Well, that's something that we denote by AXR. It's again a group generated by the elements of X, such that, well, X plus lambda X of Y, that we set equal to lambda X of Y plus lambda X of Y of rho Y of X. This looks like an ugly condition, but let's just quickly draw that. So if you start here with X and Y, you would get here lambda X of Y, rho Y of X. So what I'm doing is I'm reading from bottom to top, and crossing means apply R. So your set-theoretic solution. Then if we look at what happens at the second time applying R, we get lambda X of Y, rho Y of X. And we see that X plus lambda X of Y, so the bottom two constituents, is equal to lambda x of y plus the thing on top. So somehow this just reads what happens in the square of your solution on the left-hand component. That's all it measures. And for our solution, we assumed it's left non-degenerate, so we know that if I were to replace this guy, I'm a bit out of color. So if I were to replace lambda x of y by az, then there has to exist such a y, such that indeed this z is lambda x of y. And then this becomes a function dependent on z and x, this guy. And we rewrite this as x plus z is z plus sigma z of x. So we just get a formula for the conjugation inside this group. All right, depending on what happens in the square of your solution. Good. These two together, somehow they can talk. I won't go into that. You can construct a map from G to A, which turns out to be a bijective one co-cycle, which is data that is equivalent to having a skew brace. And so if you call this guy A for short. So that is another example, and an important example, because now we took a solution, we got a skew brace. So in some way they govern, they both generate and govern solutions, in the sense you take a skew brace, you can get a solution. You take a solution, you can get a skew brace. But this operation, well, these operations are not mutually inverse, because you can start with a finite solution. You take the structure group and you get something infinite. So you also get an infinite solution. So watch out there. It's for sure not the same solution that you would get. You would get a lot more info, or in some sense, some cases a bit less. All right. So now we've got the players, and we can take a look again at these simple solutions. So that's 5. Characterizing simple solutions. This theorem was first proven for involutive solutions by Castelli, building on work of Room. So let me just add here for involutive. You need to do, well, quite a bit of work to extend that to the non-involutive version. You need to think of need to fix quite a few arguments. So you can show that XR is a simple solution even only if, well, it's first XR can be Lubashenko, where you work with a sigma, your permutation is a full cycle of prime n. The size of X has to be a prime P. That's one case, the in some sense easy case. And then you have something that will depend on braces. So the second possibility is that it's a subsolution of the solution of a skew brace, B, such that this skew brace has to satisfy quite a few conditions. First, if you take X and you take the additive group generated by the elements of X, that should be the full B. Secondly, this B has a unique minimal ideal. I have not in detail explained what is an ideal. This is a concept that plays the role of a normal circle for people who like group theory. People who like ring theory, it looks like an ideal. And it plays the same role. It will be kernel of morphisms of braces. You can define quotients, etc. Moreover, you can exactly say what this guy has to be. This is the additive group generated by differences of elements in X. So you also feel, what does this entail? Well, if you would kill V, so if you look at B, where you quotiented out V, this will collapse the full of X, which was a set of additive generators of B. So that has to be a cyclic group. Well, has to be cyclically generated additively. Turns out that as a skew brace, it will be a trivial brace on a cyclic group of order n some integer, which is not required for the rest. The last condition is that V has an action on X. Well, because B will have an action on X actually via just applying, for example, the lambdas. This action has to be transitive. So what do we mean here is that you have to consider an action of V times V in some way in a semi-direct product where you act on X. So an element, let's say AB here, acts on an element X by sending that to sigma A inverse lambda B of X, where the sigma corresponds to the sigma we defined here with this, when we looked at the square of the solution. So it corresponds to the additive conjugation. I forgot to write this. Yes. I didn't explicitly say what this semi-direct product is. In some way, you can define an action from V, circle on V plus, through the lambdas. If you want to know more, very welcome to read our paper. It's on arXiv. Well, another thing is that this V guy, you can also explicitly say what he is. For that, you need a little bit more notation for particular elements, namely for the elements which we denote by A star B. It's a new operation because two operations in skew braces is not yet enough. You take A star B equal to minus A plus A circle B minus B. So what this measures is in some way the defect of both operations being the same, right? If B star B, so that is the, I will maybe write that, the additive group generated by the elements of the form A star B. If this guy, so this is the definition, is 0, that would mean that the two group operations coincide. In this case, because this can happen, this can for sure happen for a simple solution. In this case, V has to correspond to the commutator subgroup of the additive group. Because if this is the case, well, then this meant that you were looking in a trivial skew brace, so then this guy makes sense, and this guy will indeed be unideal, because for in trivial skew braces, unideal corresponds exactly to being a normal subgroup. Else, V is exactly B star B. All right. So let's return to this case, because these solutions, these simple solutions of this type were already looked at. They were already determined in some sense by work of Joyce and work of Andruszkiewicz, Grania, with a trick of Guralnik. Because these correspond to solutions of the form Rxy goes to y inverse xy. Remember, those were the solutions of rack type. I told you those correspond to racks, to quandles, and a solution there that is simple corresponds to the solution of a simple quandle, and they completely classify that. They classified also the structure that this group can have. So if you would then look at this particular B for such a simple solution, you can exactly write down this B as a group structure has to be very nice. Unfortunately, their very nice proof in this case does not work. Why? Well, the start of their proof is by considering the minimal normal subgroup. So for us, that would be the minimal ideal V, and noticing that a minimal normal subgroup is a characteristically simple subgroup. So this is a direct product of a simple group, of several copies of a particular simple group. And this last thing completely breaks down in the case of braces, because characteristically simple, well, you cannot measure being an ideal using automorphisms, like you can measure being normal in a group using conjugation, which are automorphisms. So that is a bit of an issue. That's why that guy breaks down, unfortunately. So at the moment, it's still an open question. Can one say more about the structure of skew braces that can appear in point 2? If you assume an easier case, for example, that b to the third, which is just b star b star b, is 0, then you can write down a complete classification. That's also in the paper. I will not give you that. That takes quite a lot of details. But in general, it's an open question. We assume it will be very hard to really classify that, because we think that a lot of simple braces can show up. But on the other hand, we also have an example where you're exactly not in this case. So where this minimal normal subgroup is not a direct product of simple groups. So that makes stuff hard. And that is indeed the thing you would aim at, the classification that looks a bit like the classification of Andruszkiewicz, Grania, and Guralnik. You would like to aim at that, but that's you won't be able to get that, unfortunately. An example, because you can, of course, say, well, it's all nice if you give a very involved characterization of how to check that a solution is indeed simple, right? Because one of the uses that you can have here is you get given a solution in the wild of a particular size. You would like to know, is it simple, yes or no? It might be very hard to identify all the homomorphic images, but maybe you can get it inside some skew brace. There are some natural candidates for this. which we call the permutation skew brace, or a slight adaptation of that, which are also explained in detail in the paper, but again, we might need a little bit more time for that. But I want to show you that actually this characterization can give you an example. Starting from a skew brace, you can then start looking, okay, are there simple solutions inside these skew braces? For example, Bayet, he recently introduced a family of simple skew braces. What did he need? Well, you needed two primes, P and Q, with a particular division condition, namely Q has to divide P to the P minus 1, but Q should not divide P minus 1. This happens in some cases, this happens in an infinite amount of cases. You can check that, but they grow very, very fast, the Q and the P. What can you then see? Well, if you look at the order P to the P, Q, there are only 3 non-isomorphic groups of this order. So you have the direct product, which we are not interested in, and 2 semi-direct products, actually, where P stands for the P group, Q stands for the Q group. And what you can show is that in both groups, you have no elements of mixed order. In particular, if you were able to put a brace structure on this, which he showed, this will be simple. So this guy and this guy can have no, let's say, common normal subgroups. Of course, non-trivial. In particular, they will not have ideals. So if we then look again at this characterization, you can see, okay, B asks that the skew brace has a unique minimal ideal, which is that guy. Well, indeed, the only non-zero that I forgot to put here, minimal, of course, non-zero, ideal, is the full brace, the full skew brace in this case. So check. If you divide that out, you get one element, which is for sure a cyclic group. Perfect. So those two are very easy. They're true. Then you can start looking for A and D. Again, V is in this case the full skew brace. So you just need to check that the action of your skew brace is transitive on the set X you choose. And the set X you choose has to be, has to generate the full group B. What you can choose in this case is, well, you take this group Q and you consider all possible conjugates. You throw out the identity element. This guy will be a nice set, and together with the R coming from the solution of the skew brace, restricted to the set X, will give you a simple solution, which is hard to check by looking at homomorphic images, but you can use these conditions to indeed see that is true. How do you see, for example, it's transitive? Well, you look at conjugates. So that is indeed particularly nice. Moreover, this Q, I told you the order was P to the PQ. So this guy is just a copy of, not CP, but CQ, of course. a copy of a cyclic group of order Q. You can show, well, the sigmas are additive conjugations, so that's fine. And your lambdas will send you to the other elements of Q. So indeed, you can have a transitive action of B on this set, and this set will generate the full of B, something you can see, you can check. Sorry. Yes. If you want a particular way to create this Q brace, you can just think of a nice vector space, a p-dimensional vector space of the field of p elements, and consider as additive group this guy in a semi-direct product with the group generated by a particular matrix, which you can show to always exist of order Q, such that if you conjugate it by a Jordan block, it becomes just the p power of n. So your additive group has to look like C p to p, semi-direct product with CQ. So this, well, again, note down, I didn't write it, has to be a simple solution. The multiplicative group, you need some more work to get that to work, to really calculate what the hell it is. And for that, please read Bayes' paper. It's a very nice short paper where he details this construction. Some problems, as I mentioned, were, well, determining the structure of such braces that can appear. Well, are there constructions for particular families of such braces? Are there constructions for such braces that then contain simple solutions? Third question is, well, we now use the simple brace. Can we bring a simple brace and try to find a simple solution inside of that? The answer to this question, we know, is no in general, but it would be interesting if there are families where this is the case, like the family that Bayet has. There are a lot of families of braces, so where the addition is indeed abelian, created by Sudo, Jespers and Okninsky. So it would be interesting to look, can we always create simple solutions in these guys? Those are some minor problems. And then I'll finish by just quickly giving a teaser of a paper we hope to publish in the next 2 to 3 weeks. Is a solution to what I wanted to say on problem D. Can you construct, maybe using these ideas, new, simple, or indecomposable solutions from old ones? For this, we extended the method made by Lebed, Ramirez, and Vendramin to the non-involutive case, which they call cabling. And this takes a solution, looks at structure groups, so the GXR. There you have particular other solutions that somehow give you more information, get you new solutions. But that's an upcoming paper that we hope to put on the archive next week, maybe in 2 weeks. I thank you very much for your attention. If there are any questions, I'm very open.
Thanks, Arne, for your very interesting talk. Are there any questions? I cannot see any questions or comments, remarks. Okay. If there are no questions, let's thank the speaker again.
Thank you. Thank you very much for having me.
And you're welcome. And we will resume on next Monday at the usual time. Bye bye. Bye bye.